Welcome back to Lesson 5 of Unit 10.
We're going to be talking about colligative properties of solutions.
Love colligative properties.
So, in case you guys are confused, please make sure you read Topic 7 in the Regents Review book. It's towards the very end of Topic 7 on colligative properties. So we'll be talking about vapor pressure lowering, boiling point elevation, and freezing point depression.
Which are all the colligative properties.
And we'll be throwing in some SAT2 stuff in there as well for you guys.
So colligative properties are properties of a solution that are assumed to depend on the ratio of the number of solute particles to the number of solvent molecules in a solution, and not on the type of chemical species present.
So this means that it doesn't matter what you're using. It doesn't matter if you're using table salt or if you're using like hydrofluoric acid. It just matters how much of it you have in your solution.
Right.
So if you notice in the picture on the left-hand side, you have what we call a pure substance. It's just one type of volatile solvent. But on the right, we're noticing now we have some sort of homogeneous mixture between the two. And you're also noticing that there's less vapor when you add the non-volatile solute into your solution.
There's also more chaos in the system too. So the quantity of particles in a solution strengthens the intermolecular force, thus lowering the vapor pressure.
So the more stuff you put into your solution, the lower your vapor pressure is going to be. Which, if you look at this graph, for example, the red line represents your pure substance. So that's going to be just regular water, for example. If you're noticing right about here, regular water has a freezing point of 0, while the boiling point of water is about 100. But if you were to add salt, like if you notice all the people on 287 are on the streets when it's wintertime, when you add salt to water, the salt is going to cause your freezing point to decrease and your boiling point is going to increase.
And that's because the vapor pressure is lowered. If you take that red line and you lower it, you're lowering it to where that yellow line is.
So when we are changing the vapor pressure, boiling point, as we just talked about, is being elevated. And the boiling point elevation describes the phenomenon that the boiling point of a liquid, your solvent, will be higher when another compound is added, meaning that a solution has a higher boiling point than a pure solvent.
So when you have like salt water, for instance, salt water will not boil at 100 degrees Celsius because the salt that was added will create an elevation of the boiling point of water.
So if we look at this chart, for example, if we were to add sucrose, which is normal table sugar, the pure water, as we notice in the far left-hand corner, with 0 molality, which means it has nothing, it has no sucrose in it, should boil at 100 degrees Celsius. But the more sugar you're starting to add as you go from 2 to 4 to 6 to 8 to 10, you're noticing that your temperature is going to be, your water sample is going to be boiling at a higher and higher temperature. So a lot of people have always asked this question, does water boil faster when salt is added to it?
No.
In reality, it doesn't. So what happens is that the salt water requires more exposure to the heat in order to boil than water alone. So the boiling point is elevated and the time it takes to get the water to boil increases. This makes the water hotter. The new boiling point is increased to about 216 degrees Fahrenheit as opposed to the standard 212 degrees Fahrenheit for unsalted water. But it doesn't make it boil faster.
The pasta might cook faster because it's warmer.
Yeah, the pasta will cook faster because the water's hotter, but there will be no like immediate quick response to the water going from cold to boiling. It actually, like it says, will take longer than expected.
Mm-hmm. So now freezing point depression is the phenomenon where the freezing point is actually lowered when you add a solute into a solvent.
And some examples of this would be if you add salt to ice, that's why ice will melt in the presence of salt in the wintertime. Mm-hmm. Or, for example, why alcoholic beverages do not freeze if they're put into a freezer. So one way of visualizing the idea of freezing and boiling points and how they are changed on a molecular level is kind of like an airport. So if an airport was empty, like a pure solvent is just all one thing, if it was empty, you can go from like the parking lot to your terminal relatively quickly. But as you start to add more solute or more ions into your solution, that would be like adding more and more people to the airport. Eventually, when there's so many people in the airport, it's going to take you a lot longer to get to your destination just because of the fact there are people, or in chemistry, there are ions physically in your way.
So now we have the ion effect on colligative properties. The more moles of ions that we have dissociated in a solution, the greater the change in freezing point and boiling point of the solvent.
What does dissociated mean?
Dissociate means to separate. So if the ions separate in water, or if, for instance, a covalent compound is not going to dissociate, it's just going to push around inside a solution. But the more that we can get dissolved into the solvent, it will create more moles, and more moles creates a difference of colligative properties.
So the more moles of ions we have, the bigger the effect, right?
Right.
Okay. So if you have 1 mole of sodium chloride, then you only have 2 moles of ions.
Right, because the sodium chloride is going to dissociate or separate into Na plus and Cl minus.
And if you have 3 moles of calcium chloride, you have 3 calciums and you have 6 chlorines.
Right, because there's 2 sets of chlorine per 1 mole.
Oh, but we all know that covalent compounds, though sugar, for example, dissolves in water, does it dissociate? Does it actually split apart?
It doesn't split apart.
So if you put 1 mole of sugar in, how many moles should you have aqueously?
You still only get 1 mole.
Oh, and if you have, let's say, 3 moles of ethanol, which is CH3CH2OH, you still only have 3 moles because these guys do not dissolve.
Right.
So let's try this question. Of the 5 different samples, which solution would have the highest boiling point, or which one, hint, hint, is going to be or have the most amount of ions when dissolved?
Right. Now, molarity, which is the capital M, does play effect to this because there's going to be twice as many or twice as less or whatever you want to call it.
So if you have 0.1 molar and you have 0.2, obviously the 0.2 has double the strength. All right, so take 20 seconds and try to get this problem. All right, you guys should notice that it's D. D says that you have a stronger molarity, and calcium chloride, when dissolved, is 3 ions. Now, you can also say, well, what about Na2SO4?
Yeah, that also did have 3, but it's 0.1 molar.
Thus, that's why D is the correct answer.
Yep.
Stronger solution. So now let's talk about how do we actually solve these colligative properties. This is for the SAT 2 course and for the Regents kids that want that extra challenge. So the amount of solute, the amount of substance you put into your water, has a direct effect on the boiling or freezing point of a solution. This is a formula you need to write down. Delta T, or the change in temperature for the freezing point, is equal to the constant for freezing times the molality of your solute times the number of ions. Your constant for freezing, which is called the molal freezing point depression, specifically for water, is 1.86 degrees Celsius per molal.
Okay, and that number will be given to you on the SAT 2. They add it in their questions.
You don't have to memorize this, but for our course, you do have to memorize it.
Right. Now, you can do the same formula, but for boiling. So where it says freezing, just substitute the words boiling, and then the constant for boiling is going to be a little bit lower. It's going to be 0.51 degrees Celsius per molal.
And you're noticing with this formula, it's kind of simple. You're plugging in that number times the molality of your solute times the number of ions. Just remember, when you have your ions, if it's ionic, dissolve it, write down how many that is. It could be 2, it could be 3, it could be 4. But if you have a covalent compound, it will always be 1 because covalent compounds do not dissociate.
And polyatomic ions count as one whole ion themselves.
Like SO4, that's 1 ion.
So now try this one. Calculate the freezing point and boiling point of a solution of 100 grams of ethylene glycol, which is C2H6O2, in 900 grams of water.
Now this is going to be about 3 parts, so let's do this together. The very first thing we have to do is calculate the molality. All right? So we know we have 100 grams of ethylene glycol, and we know its formula is C2H6O2. So the first thing we have to do is say, well, what is 1 mole equal to? 1 mole of ethylene glycol is equal to 62 grams. I have 100 grams, so when we set up our proportion, we should realize that the number of moles we have is 1.6 moles. We're going to be using now 1.6 moles, and you divide it by your total amount of solvent, which is 0.9 kilograms, and that tells us we have a 1.79 molal solution. We're going to be using that number now for the rest of our calculations.
And this was the same formula you learned in the video from last night.
So using our 1.79 molal calculation, we are now going to be looking at the changes in freezing point. So again, we're using our 1.79 molal, and we're going to be using it with the formula that we just got on the last slide. So the delta T of freezing, which is the changing in freezing point, is equal to the constant of freezing times the molality, 1.79, times the number of ions found in ethylene glycol. We know that our constant for freezing is 1.86. We also know the molality we just calculated is 1.79. And because ethylene glycol is a covalent, compound, there is only one thing to it. So when you take 1.86 times 1.79 times 1, you get a change in freezing by 3.33 degrees Celsius. This means that your new freezing point is a negative 3.33 degrees Celsius. Why? Because the freezing point of water originally was 0, and now because we're changing it, we are decreasing it by 3.33. Now let's solve for the boiling point change. Again, still using our molality of 1.79, we're going to be now using the change in boiling point formula. So our delta T is equal to the constant of boiling, which is 0.51, times the molality, which is 1.79, times 1, because it is a covalent structure. And we notice now we have a 0.91 degrees Celsius change in the boiling point. What's the boiling point of water? Well, that's 100. So 100 plus 0.91 tells us that we have 100.91 as our final new boiling point. Now you may be saying, why are we not subtracting? Well, boiling point elevation means you are increasing the boiling point by elevating it. And a freezing point depression means that it is going to be less. Alright guys, so tonight's video we talked about colligative properties. We also talked about vapor pressure changes, how to calculate through boiling point and freezing point, and for you SAT2 kids, we actually know what we should be doing when we do that math. Other than that guys, have a great night.